Okay, this is Chapter 12, Analysis of Variance, or ANOVA. And before we get into the lecture, I want to read a few paragraphs from The Lady Tasting Tea to kind of set the stage. Ronald Ulmer Fisher was 29 years old when he moved with his wife, 3 children, and sister-in-law into an old farmhouse near the Rothamsted Agricultural Experimental Station north of London in the spring of 1919. By many measures, he could have been considered a failure in life. He had grown up as a sickly and lonely child with severe vision impairment. To protect his nearsighted eyes, the doctors had forbidden him to read by artificial light. He had taken early to mathematics and astronomy. Sir John looked at this vast collection of data and decided that maybe somebody might be hired to see what was in it, take a sort of statistical look at these records. He inquired around, and someone recommended Ronald Ulmer Fisher. He offered Fisher a year's employment at £1,000. He could not offer more and could not guarantee that the job would last past that 1 year. Fisher accepted Russell's offer. He took his wife, sister-in-law, and 3 children into the rural area north of London. They rented a farm next door to the experimental station, where his wife and sister-in-law tended a vegetable garden and kept house for him. He put on his boots and walked across the fields to Rothamsted Agricultural Experimental Station and its 90 years of data to engage what he was later to call raking over the muck heap. And it was this experience, really, that motivated the idea of ANOVA in the first place. And I think it's interesting to point out that the real motive for this statistical method has agricultural roots. And, the people at this research station had been collecting data on weather, temperature, rainfall, all sorts of different things for the last 90 years. And it was just a massive amount of data. And Fisher was able to tease it apart. And one of the major methods he came up with is what we now call ANOVA. And ANOVA stands for Analysis of Variance. And ANOVA is a hypothesis test for population means when we have more than 2 populations, or 3 or more populations. And the general statistical hypothesis looks like this. The null assumption is that all the means are equal. And you notice the subscript on the last mu is I. And I is equal to the number of populations. The alternate assumption is that not all the means are equal. So the alternate here is not very specific. All it says is they're not all equal, or at least one of them is different than the others. Here's an example to motivate the idea of ANOVA. And the question that we're going to try to answer is, does package design sell more cereal? So here's the story. The Kenton Food Company wished to test 4 different package designs for a new breakfast cereal. 20 stores with approximately equal sales volumes were selected as the experimental unit. Each store was randomly assigned one of the package designs, with each package design assigned to 5 stores. A fire occurred in one store during the study period, so this store had to be dropped from the study. Hence, one of the designs was tested in only 4 stores. The stores were chosen to be comparable in location and sales volume. Other relevant conditions that could affect sales, such as price, amount, and location of shelf space, and special promotional efforts, were kept the same for all the stores in the experiment. And so these variables that we're talking about, price, location, promotional efforts, these are all what we call confounding variables. So in the experimental design, there was an interest in controlling the confounding variables, which is good, of course. So the hypothesis here is that all of the mean sales amounts are the same, and the alternate is that they're not all the same, or they're not all equal. Like all hypothesis tests, all we need now is a p-value. So here's the data. So across the top, we have the 5 different stores for each design. And then we have the number of cases sold by each of the stores. So what we're going to compare is the average number of cases sold in each of these stores. I want to show you first of all how to do the, actually we're going to do the number crunching we're going to do on the calculator. So the first thing I want to do here is enter the data into the calculator. And for convenience, I'm just going to use L1 through L4. So I press Stat, go to Edit to take me to this data editor. And I have some data in these lists, so I'm just going to take a minute here and clear out all this data. Start from some fresh, empty lists on the calculator. So let's see, in L1, store 1 sold 11 cases of design 1, and store 2 sold 17. So just entering the data. I'll go on to package design 2, and 12, 10, 15, 19, and 11. Package design 3 was not all the stores were able to finish. One of them had a fire, so it was knocked out. So there are only 4 data values for design 3, but we can still do ANOVA. It's just not what we call a balanced design. When each level has the same number of data points, we call that a balanced design. But only missing 1 store out of all of these different options is not a huge deal for the ANOVA procedure. In any case, so have the data in the calculator now. We'll come back to that in a minute. Here's the basic way we do this on the calculator. We press Stat, we go to Tests, and then we go all the way down to H for ANOVA. Oops. So again, going back to the calculator, the next step would be to go Stat, Tests, the very bottom one. I'm doing an up arrow because I remember that the very bottom option in Tests is ANOVA. So I'll select ANOVA. Now, here's the syntax. ANOVA, parenthesis, and then each of the list names separated by a comma. So I'm going to put L1, comma, L2, comma, L3, comma, L4, close the parentheses, press enter, and the calculator spits out all this different information here. And so we'll come back to some of what these different things mean later on, but for now I just want to stick with the main idea. Now notice here's the p-value. So I hope you're noticing in this class that everything seems to come back to a p-value. And so let's see, again, let's remember that. I forgot what the p-value was. Let me see. I know it was small. It had something times 10 to the 5th there. 2.5, 2.6 times 10 to the 5th approximately. So now let's see. Let me write down this p-value. So the p-value is about 2.6 e negative 5, which means 2.6 times 10 to the negative 5th. That's scientific notation. So move the decimal 5 places to the left, and what you see is a very small p-value. And that very small p-value implies that the data are highly significant, and we only have significant data when H naught was rejected. So basically, this p-value is telling me to reject the null hypothesis. Now, if we go back and remember the statistical hypothesis, the null for ANOVA is always the same. All of the means are equal. We've just done the calculations on the calculator. We just did an ANOVA analysis on the calculator. And what we found is that not all these means are equal because we've rejected the null in favor of the alternate. Now, there's a little bit of a problem though, as you might imagine. We can't tell from ANOVA which particular mean was different than the others. So the p-value tells me that for at least one package design, the population mean was significantly different than the others. Now there's a method we can use to help distinguish, to do two things really, to help distinguish which of those means might be the one that's different, and also to give a kind of a synopsis of how ANOVA actually works. So what I want to do here is create some confidence intervals. 95% confidence intervals. So again, I'm going to go back to the calculator here and, whoops. Let's see if I can do it from here. Oh, I can do it right here. All right. Hit the wrong button. I want to remind you how to do a t-interval. Now remember, we have a small sample size. We don't know any of the standard deviations here for the population. So we're definitely in the realm of t-distribution land. And so I'm going to go down here to t-interval. And basically what I want to do, and again I have data, so I'll leave that data selected here. And we'll start with list 1. I'm going to just create 95% confidence intervals for the population mean. Now that makes sense because ANOVA tests a hypothesis about population means, and now we're going to look at this analysis in a slightly different way. And we're going to look at confidence intervals for each population's population mean and see, and then I'll show you what to do after that. So I'm going to say calculate here, press enter. All right, so what I have is a confidence interval for the population mean for the first box design number 1. And another little subtlety I'm going to bring up here, and this is not a huge deal necessarily, but when we round with confidence intervals, the convention is to always, and we don't actually follow the scientific rules for rounding, the convention in statistics is to always round the lower limit down no matter what, and to always round the upper limit up no matter what. And the reason for that is because what rounding can do, and again, this is sort of a mathematical subtlety really, but what rounding can do is affect the level of confidence. Because remember, the level of confidence is tied to how wide the interval is. So if we make our interval artificially wide by rounding, then what we've done is technically we've lowered the level of confidence, or vice versa. So basically what we want to do is make sure that we always have our confidence intervals slightly wider than narrower, so we preserve the level of confidence. So I'm going to call this interval 11 to 18. And so the interval estimate for the group 1 group 1, which is serial box design number 1. The confidence interval was 11 to 18. I guess it was crates, right? And again, I'm going to do all of the groups here. Whoops, I'm just going to write them down because I won't go through each one on the calculator. But I've already done the confidence intervals for all 4 groups. So let me just write them down here. So I got 8 to 18 for group 2 and 15 to 24 for group 5, or it's group 3, I mean. And well, let's see, group 4 is 22 to 33. So just by looking at the confidence intervals, you might kind of begin to see what's going on here. It appears that group 4 is quite a bit higher than the others in terms of the confidence interval. Now, another way to say this, or to see this, is by looking at these confidence intervals, as a graphically, or we might even say spatially. So what I'm going to do here is create a scale on my axis, 5, 10, 15, 20, 25, 30, 35, say. And I just noticed that I actually drew, let me change my scaling here a little bit, even 5. I'll go 10, 15, spread this out a little bit, 20, 25, 30, 35. And the label I'm going to put on this axis is X bar. So these are all sample means. All these confidence intervals are based on sample means. Now basically what I'm going to do here is I'm going to draw the confidence interval. So the first confidence interval starts here at about 11. So I'm going to put a little parenthesis here. I'm going to go down here to 18 roughly. And again, it's a sketch, so I'm going to do, I want to do a reasonably good job. And then I'm going to just demonstrate, or draw the confidence interval. Now, the idea here is that this is really, I could just project this down. In other words, when I draw that confidence interval, what I'm really talking about here is the open interval between 11 and 18. And I could shade that on the axis, but I'm just going to raise that up here above so we can see them all together. Now, the second group had a confidence interval that started here at about 8. It went to 18. And group 3 started at 15 and went to about 24. And then group 4 started at about 22 and went to about 33. So again, the ANOVA part of the analysis was looking at a statistical hypothesis that all 4 population means were the same, and then the alternate is at least one's different. And our small p-value, I'm not going to write it down again. Our p-value was small, though. It was less than 1 in 10,000. So it was highly significant. So we did reject the null hypothesis here that they're not equal. But ANOVA can't tell us. ANOVA by itself can't tell us which mean is different from the others. So in a sense, what we can tell from ANOVA, or all we can tell, without some, I should really preface this and say there are advanced techniques in ANOVA where you can actually tell which of the means is different, but they're very sophisticated and beyond the scope of this class. And so to keep things simple, all I'm going to say in this class is that ANOVA on its face as a method cannot distinguish between those means or tell which one's different. But what I can see when I look at these confidence intervals, and especially when I look at them graphically, is that box design number 4 really seems to be the one that's selling more cereal. And what I'm doing now is I'm just going to put the sample means in here as well, because I've got the sample mean number 1, sample mean number 2, and sample mean number 3, and sample mean number 4. And all those sample means, oops, I said 3, that's 3, and sample mean 4. And all these sample means are estimating the population means, or their respective population means. So what does ANOVA do? ANOVA compares the variation between the x bars to the overall variation among the populations. Okay, so all right, what does that mean? Well, take a look at all these sample means first of all, okay? What do we mean by variation between these sample means? Well, if I kind of draw these dashed lines through here, maybe what you can see is that these means are all varying amongst themselves. In other words, there's variation between all of these different sample means. And then the other thing to notice is that some of these confidence intervals actually are not overlapping with each other. Specifically, box design 1 and 2, they don't overlap with box design 4. And so the reason we're getting such a small p-value is because the variation between those sample means is exceeding the overall variation within the samples themselves. Now, just as a mathematical side note, sometimes students ask me, why not just do sets of t-tests? In other words, why not just do 2 population t-tests here? And you know, because really in a sense, that's kind of what I'm alluding to with these confidence intervals. Like I could say, you know, I could have a hypothesis that says mu1 equal mu4. And then the alternate would be mu1 is not equal to mu4. And I could do a 2 sample t-test for independent samples. And it's true, I could do that. But I would need to test 4 different groups. It would take 4 choose 2 combinations of t-tests. And that's equal to 6. So overall I'd have to do 6 different t-tests in order to come up with the particular, you know, in order to test each one of these particular means with each other. Now, the problem with that, ultimately, the problem with that is the fact that if we were to do it this way, we couldn't say our level of significance is 5%, say, even though you may have learned that a 95% confidence level implies an alpha of 5% for a 2-tailed test, and that's true. But the problem here is that we're not just doing 1 test, we're doing 6. And so what actually happens is the confidence level for our overall system, oops, this should be 9.95, is actually equal to 1 minus 0.95 to the 6th. And again, I'm not going to get into all the mathematics here about why that's true. And if you're interested in why that's true, then I would strongly encourage you to take, more stats courses. But what we end up with actually is a confidence level that actually drops down to about 26%, or about 26%. So really the problem is when you combine 6 different hypothesis tests together, your alpha goes way up, meaning your type 1 error rate goes way up. And again, that's a big problem in ANOVA, or I mean in statistical hypothesis tests. It means if we were to just use these confidence intervals, for example, instead of ANOVA, instead of having a p-value less than 1 in 10,000, our p-value would have to be, well, we wouldn't have just one p-value either. That's part of the problem. So I'm not even thinking about alpha. I'm kind of comparing apples and oranges, but, or I don't know if it's apples and oranges. I don't want to get hung up on those semantics. But in any case, so a p-value, let me just be clear here, a p-value this small means alpha could be less than like 0.0001. So our alpha here, type 1 error rate, could be very, very small with a p-value this low. But if I go back and talk about that system of 2 population t-tests, then alpha would go from 0.5 all the way up to about 26%, which is, now we're saying our type 1 error rate is about 1 in 4. And that's too high. So what is it, how do I summarize this all together? Well, as a general, the way I like to do ANOVA, and again, this is called one-way ANOVA, which is the only kind I'm going to cover in class, but the way I like to do ANOVA is I do the ANOVA test with the null and alternate, the traditional null and alternative hypothesis, like this, get a small p-value, and then as a demonstration, I draw this graph. Now, I can't use this graph to establish statistical significance, but what I can use this graph to show a reasonable person is it sure as heck looks like box design number 4 is the one that's causing the rejected null. So let's talk a little bit about the transformation and the test statistic and the distribution, okay? Now, ANOVA relies on something called an F-statistic. And the F-statistic, to keep it really basic, the F-statistic is a ratio of the variation between the sample means to the natural variation within the samples. And so what ends up happening here is that as the numerator becomes large, the denominator, say, is small, a large number over a small number is a large number. Now, the F-test, the F-statistic, the F-distribution, I should say, this graph down here shows the F-distribution, is a one-sided direction of extreme always. Because again, what we're saying is we're going to reject the null when the variation between the sample means is really large relative to the natural variation within the samples. So our p-values for these tests are always going to be calculated looking at a right side direction of extreme. And notice you can see the general shape of this F curve. F values within the range, F values, there's a typical range of F values. What just happened there? Hold on. I want to change my pen color. All right. So there's a natural, kind of a typical range. This would be consistent with H naught. And then there's the extreme values of F out this way. Extreme values. And again, there's going to be some particular value of the F statistic. So this is the F we would get from data. And so then again, like I said, the p-value is always going to be the right tail area. So the idea here is very similar to all of our other hypothesis tests where there's this threshold of extreme for F. And when you cross that threshold, now, well, I should say that a different way. This is measuring as extreme or more extreme. Because again, there's two different ways to look at this. The p-value is a measure of, tells us what proportion of the distribution of F statistics would be as extreme or more extreme if H naught were true. There's also alpha, and alpha is going to be based on this threshold idea. So another way to think about this is we could define an F critical value, say, that defines our decision rule. So we're going to reject H naught if F from the data is greater than or equal to F critical based on whatever alpha. Now the alpha here is going to be the area. I'm going to kind of do a dash line here. That whole area out in that direction would be alpha. So you can see if P is less than alpha, like I'm indicating in this graph, we'd be rejecting the null hypothesis. And, you know, I should also mention that if you're going to do ANOVA as a professional, you're going to need to take really a class on ANOVA. There's a whole semester, well, at least a semester's worth, probably even more than, way more than a semester's worth of knowledge that's available on ANOVA, and there's all different kinds of ANOVA. In any case, but again, in this class, we're keeping it pretty straightforward and simple and just looking at one-way ANOVA and the basic ideas. Let's take a look at another example here. And this is an example on red dye number 40. Let's see, S.W. Leogkos and F. Mosler of Harvard University fed mice different doses of red dye number 40 and recorded the time of death in weeks. Results for female mice, dosage, and time of death are shown in the data. So here's our data. And so we have four different levels here. We've got the control group. They weren't given any dye. We have a low dosage, a medium dosage, and a high dosage. And so here's our data again. So let's enter this data into the calculator. First thing. All right, so let me set my window up here, hopefully, so we can see both the calculator and the data. All right, now I'm going to go to the data editor. And I'm just going to clear out this data from the other example I did. And I do like using L1, L2, L3, L4, the built-in list, because there's kind of a built-in group number system, right? So I have 4 groups, L1 through 4, and then I can use L1 through L4 and kind of help keep track of what data goes where. All right, so I'm going to enter the data. so I got the first three columns of data entered here, and I'm going to double check them. So I'm just going to go, I like to go from the bottom. Oops, let's see here. Bottom from the top. I should be able to check these three rows. So, oops, wrong arrow. So I got 110, 88, 93. Okay, those three columns look good. Let me enter L4 now. All right, let me check this. Okay, looks good. So we have the data entered into the calculator. So let's go ahead and jump in, and we'll just go straight to the ANOVA. Now, I'm going to quit out here to the home screen. I'm going to show you a trick. Now, the last thing I did on my calculator was an ANOVA. Now, I could go to Stat, Test, and find ANOVA again, or as a shortcut, I can just go second enter. The calculator actually brings back the last ANOVA command. I just entered new data into L1 through L4. So the p-value I'm getting here is a different p-value. So again, we have a small p-value. Our p-value is about it's about 8 times 10 to the negative 7. Oops. All right, let me do it here. So, okay. So let me write down the p-value here. And again, that p-value is tiny, and a lot of researchers would just write that p-value is less than 0.0001, which means it's highly significant. Now, the situation looks like this. So the null is that each of the 4 different levels, or each of the different populations of mice, it's 4 different populations of mice, each with a different dosage of red number 40. So again, we had, just to remind everybody here, we had group 1 was our control. This was low dosage. This was a medium dosage, and this was a high dosage. And again, this p-value says that at least one of these means is different from the other. All right, but this is a pretty vague, again, a pretty vague looking hypothesis here, or alternate. So we know we're rejecting the null, but what are we rejecting the null in favor of? Can we look at these confidence intervals again and get a better idea for which particular treatment group had the significant difference? So let me set up a scaling here. So we're going to go 40, 50. All right, So my axis is a little bit crooked, but it's 40. And the confidence intervals look like this. So the group 1, remember this is how long they lived. Average number of weeks is what we're trying to estimate. The first confidence interval, and I'm not going to go through the calculator steps again for drawing these or for creating these intervals. I did this ahead of time. So this first confidence interval here is kind of telling the tale. All right, these two groups seem to be significantly different from each other. So in other words, the control group compared to the low dosage group have confidence intervals here that aren't overlapping. Let's take a look at the other two confidence intervals. So when I look at the other two confidence intervals, I see something quite interesting here. And that is that it looks like now when I look at all these things together and start thinking about the ANOVA analysis of variance, which again is comparing those sample means, how much variability there is between these sample means to the overall variability within each of the samples, we have an issue here. Now, it seems clear from this graph that the variability for the control group is much lower than the variability for especially the high dosage group. Some of those mice did not live very long compared to the others, and there's a wide variation there in terms of lifespans. And that violates a basic assumption of ANOVA. So this particular analysis does, give us a very, very small p-value. So the ANOVA part of the analysis says that the results are highly significant. And when I compare the confidence intervals, it seems clear that the control group has way less variability within, and the sample mean is significantly higher than the other three means. However, here's the issue. Group 4 has this wide variability. This very wide variability here is indicating an issue with the ANOVA assumptions. So let me take a second and go through the assumptions here. So the idea is that we've got I populations, and we're going to take random samples from each one of those populations. Now look at the notation very carefully, because one of the things I've pointed out in an earlier lecture is happening here as well. You see each one of these sigmas does not have a subscript. And so what's subtly implied here by the notation is that all the population standard deviations are the same. And we can see the same things happening here. So the assumptions behind ANOVA are that we have a random sample. There's a random sample again. So we don't have bias in our sampling. N1 is the sample size for group 1. And that sample came from a normally distributed population with in each one of the samples comes from a normal population, and all of those standard deviations are equal. So a key assumption with ANOVA is the population standard deviations are equal, and we call that estimate the common population standard deviation. Now, I could go on and on and on with the details behind ANOVA because, again, you can dig down deeper and deeper and deeper, and things get more and more and more complex. But the one last mathematical thing I'd like to say about ANOVA is that this equal variance assumption, you might recall from the two-sample t-test process for independent samples. So notice here, again, we have independent samples, like in that case. And if you recall, the question about sigmas came up when we were trying to decide, do we pool the standard deviation or do we not pool the standard deviation? So for ANOVA, the reason we have this this assumption is because we always pool the standard deviations. Okay, therefore we have to have sigma 1 equals sigma 2 equals sigma 3. This is the homoscedasticity assumption, and it's the same assumption from the two-sample t-test. So that is a connection back to two-sample t-test. But again, we need to use ANOVA when we have more than two populations, 3 or more populations, and it's because of the eroding alpha situation that we have. So anyway, we're not going to spend a whole bunch of time in class on ANOVA. This is pretty much it, and I think I've only given you like one homework problem. ANOVA is an amazing area in statistics, but again, it's very broad. I highly recommend, if you want to be a statistician, that you take a course, an entire semester course on ANOVA in and of itself. In any case, that's it for this lecture.